Now let's see why append is tail recursive. We're going to do this by using the kernel language. We're going to translate append into the kernel language, and then you'll see how it executes. So let me bring in a kernel language definition here. So remember, we talked about the kernel language in the first lesson. So the kernel language is this small, simple language inside of each paradigm that shows the essential concepts of the paradigm. So any full practical language using that paradigm can be translated into kernel language. So with this, we can see exactly how the execution happens without all the complexities of a practical language. So here, let me show the definition of the kernel language of the functional paradigm that we saw so far. We have the instruction S here. So this is a grammar definition. And this is defined as the possibilities on the right-hand side. So we've seen sequential composition, when one instruction follows another, local, where we introduce a local identifier, binding of one identifier with another, or of an identifier with a value, the conditional if, the procedure declaration, the procedure call, the case statement. Notice there's some interesting points here. Look at the list definition here, and the definition of patterns is exactly the same as that of lists. Notice that in addition to the recursive X bar list, we have this extra identifier here. Why do we have that? Well, it's because we can create lists incrementally. You can have a list pair where we have an identifier, which is a variable, bar, another identifier, and the second one we bind it later. So if we do that, well, the grammar, of course, has to take that into account. So the list is slightly more general. So this is the kernel language we saw so far. And now let's translate append into this kernel language. Now notice in the kernel language there are only procedures, not functions. So why is this? Well, procedures and functions are very similar to each other. The only difference is that a function returns a result and a procedure does not. It has some action. But we can easily model a function as a procedure by adding one extra argument, by passing the unbound variable and binding it inside the body, and that corresponds to the function result. So the append, let's define it here, will be therefore a procedure with 3 arguments, L1, L2, and the output of the original append function will be added as a 3rd argument in the procedure. And now let me use instructions from the kernel language. So case L1 of nil, then the result, L3 is equal to L2, else. Notice that the case statement in the kernel language only has one pattern. So if we have more than one, we have to have another case, L1 of H1 bar T1, then, and now it's interesting, we have to do H1 bar append T1 L2. So in order to do that, since there's a result of the append being passed to the list creation, we have to introduce a local identifier. So we need a local T3 in. Then I do L3 is equal to H1 bar T3, and now a recursive call append of T1 L2 T3. And now let me close the instructions with ends. So we have here a new definition then of append. Let me feed it to the system. Now we can call this, and as we'll see, it will give the same result as the other definition of append. Notice here to the left. And in fact, a very interesting property that we have in the kernel language in Oz is that the kernel language is a subset of the full language. And this means that you can write programs in the kernel language. You might not want to do that for various reasons, but you can do it. And sometimes it's interesting to see what happens by doing that. So if you look here in this particular definition, notice this append call, this append procedure with 3 arguments, T1, L2, T3. So what happens is the T3 is an unbound variable here in the local, and then it's unbound here in the list creation, and it's passed as unbound in the append. So the execution of the append here will bind it, and that's the output of the append function.